Okay, so the next thing that we're going to do is to take and turn our secant squared, because we're going for just plain tangent here, right? That's all that we're looking for in this is our tangent squared. So I'm going to take this secant and use the properties of reciprocals, and we know that this is 1 over cosine squared. And we're going to leave our sine squared as just negative sine squared x over 1. And we'll multiply these two things together. And what we're going for is negative tangent squared. And when we multiply, we get negative sine squared over cosine squared. We're trying to prove that this equals negative tangent squared. And sine over cosine is tangent, so sine squared over cosine squared is tangent squared. And there is a negative. So this is negative tangent squared x equals negative tangent squared x. And this thing checks. All right, so that is example 3. Let's move on to example number 4. And this is tangent x, that's an n, plus cotangent x equals secant x cosecant x. And it's always easier here to deal with addition and subtraction. This is actually the more difficult side if you're unsure. So we can always add like terms and get these into like fractions. So what we're going to do here is turn our tangent and cotangent into sines and cosines. So tangent will be sine x over cosine x. And then cotangent is cosine over sine. And then we want to prove that this equals secant cosecant. And now these are multiplied on the right-hand side, right? Well, you need a common denominator here. So I'm going to multiply this one times sine and this one times cosine. And remember, when you do this, you're actually multiplying top and bottom, right? So I'm not really showing that. I like to show it on the top and not really the bottom. So what we end up with here is a sine squared x plus a cosine squared x. And the whole idea is to combine it over one denominator. So this gives me a cosine x sine x. And I'm going to try to show that this is secant x cosecant x. All right, well, by a Pythagorean identity, sine squared plus cosine squared is 1. And this is over cosine x sine x. We're going to try to show that this is secant cosecant. And I can break these up here into two separate fractions. So this is 1 over cosine times 1 over sine. And then 1 over cosine is secant. And 1 over sine is cosecant. And that proves the left side equals the right side. And that one's done. All right, let me flip my page here. Hopefully this isn't too loud. Okay, example number 5, new screen. Again, we're just going through a bunch of different examples here because the more of these you see, the more of these you try, the better and better you're going to get at them. So this one is secant x plus tangent x equals cosine x over 1 minus sine x. And here, the right-hand side is the more complicated side. And you've only got single terms in the denominator. I'm sorry, you have double term in the denominator, but the sign isn't squared. So you can't use a Pythagorean identity here. And the reason you cannot use the Pythagorean identity is because the trig function is not squared. right? And all of those, you were like sine squared plus cosine squared is 1, secant was squared, tangent was squared. Well, that doesn't happen in this one. It's just a sine x. It's not a sine squared x. So you can't use a Pythagorean identity here. This does not equal cosine squared. It would be really nice, but it doesn't happen. So when we have something like this, a common method of something that you can do is to do what's called multiplying by the conjugate. And what that means, the conjugate is the denominator with the middle sign changed. And what we're going to do is we are going to multiply the top and bottom of the fraction by the conjugate. Okay, so I'll show that in green up here. What I'm going to do is I'm going to move this red comment just a little bit. Excuse me. When I talk a lot, it doesn't always work very well. I don't know, maybe it's too many years of teaching and talking too much. All right, so my conjugate is the denominator with the middle sign change. So 1, I need a pen. I'm going to sneeze again. Excuse me. Excuse me. So we have 1 plus sine of x. 1 plus sine of x. Now, when you do this, make sure you put some parentheses around all these things. And then we're going to distribute on the top. And we're going to FOIL on the bottom. All right. So I'm going to, I guess, do that down over here. It's going to be weird, though. Nah, I don't know. Yeah, it's going to happen down there. I'll do that in blue so it stands out. All right, so we're going to multiply the cosine x by 1. And then we're going to get actually, maybe we should just leave that. Sometimes the best thing to do is to leave your numerator in its factored form and don't multiply things out until you know if it's going to be useful or not. So I'm going to leave this like this for now. And then we'll FOIL out the bottom. So I get a 1, and then my positive sine x and negative sine x will cancel each other out, which is the point of your conjugate. That should always happen. And then we get a negative sine squared. So the point in us doing this, you may now recognize, is that this is now a Pythagorean identity. And it allows us to replace this whole denominator with cosine squared. So now I have cosine x times 1 plus sine x over cosine squared x. Okay. And I'm going to now take and cancel a cosine on the top, cancel a cosine on the bottom. Well, this is going to leave me 1 plus sine x over cosine x. And now when I have one term in the denominator, and again, you may remember from the, was it the beginning of this lecture? I think it was, the guidelines for verifying trig identities. Step number 2 talked about trying to create a monomial denominator. And that's what this means right here. Monomial denominator. Right? One term in your denominator, because there's a rule of fractions that says a over b plus c over b equals a plus c over b. Well, what we have right now, we have this, one fraction over one denominator. We have 2 terms in the numerator, 1 term in the denominator. And what we're going to do is turn it into 2 fractions. so that, look what we're going for. We're going for two fractions right here. So we want to go ahead and separate these things. So I'm going to do that. I'm going to go back to a pen, and I'm going to separate these guys into 1 over cosine plus sine over cosine. And that's how you do that. Each numerator term over the same denominator term. And when I do that, 1 over cosine turns into secant, and sine over cosine turns into tangent. And that is what we were going for at the beginning. And that thing checks out. Okay? So that was example number 5. So we have 2 more. We have example 6 and then example 7. So hang in there. We're getting close. All right. Example 6. All right. This guy looks like cotangent squared theta over 1 plus cosecant equals 1 minus sine theta over sine theta. All right, well, we're going to work with the left-hand side. And the reason we're going to work with the left-hand side is because of our squared here. That gives us the availability to use a Pythagorean identity. So this Pythagorean identity is cotangent squared is 1, cosecant squared minus 1. And we're going to put that over 1 plus cosecant. And we want to show that this equals 1 minus sine over sine. All right, now this is a little strange step here, but these guys are all difference of squares, right? So I'm going to factor. And again, this is just, you may not think of this off the top of your head, but this is the reason I'm trying to point these things out and do all these different examples, is so you start to see different things, go, oh, remember when she factored that? So I can factor this into cosecant theta minus 1 and cosecant theta plus 1. And we talked about factoring in the last lecture, maybe 2 lectures ago, I don't remember. And we're going to put this over 1 plus cosecant theta. Well, remember when you add, you can turn things around. So these 2 terms, cosecant theta plus 1 and 1 plus cosecant theta, those are actually identical to each other. And now this leaves us just cosecant theta minus 1. And let's see, what do we want to do with this guy? We need this to look like this. 1 minus sine over sine. And we don't have any sines. We only have cosecants. So the best thing for us to do right now is to turn this guy into 1 over sine. And then if we want a common denominator, we can turn this 1 into sine over sine. Right? Again, you're turning numbers into words, which is a little strange. It takes a little bit of getting used to. We're trying to show this. Again, you're just bringing this right-hand side down the whole time. And now look what happens. We have on the top here 1 minus sine theta, because we have the same denominator, over sine theta. And that's what we were trying to show. So I like to say, if you try to keep where you're going in mind all the time, we had cosecants over here, but we need sines. So if you kind of keep what you have in mind, and cosecant and sine are reciprocals of each other, then you're close. You're super close. You just need to go a little bit further. Also, in case you've forgotten where we are, this is 7.1b for the bottom of your page. All right, example 7 is an A and a B, and then we're done for this lecture. So example number 7. A is tangent to the 4th, x is equal to tangent squared x secant squared x minus tangent squared x. Well, this came out of my old textbook, and they actually do this a very different way, but the way that I saw to do this, on the right-hand side, there's a tangent squared x in both terms, so let's factor that out. tangent squared x, and that leaves me a secant squared x minus 1. And secant squared x minus 1 is tangent squared by a Pythagorean identity. And tangent squared times tangent squared is tangent to the fourth. And you were trying to show that it's tangent to the fourth. So that one's done. Okay. And part B is a little bit wackier, but it's something that you should see because you definitely have to do it in a problem somewhere. So sine to the third or sine cubed times cosine to the fourth is equal to cosine to the fourth minus cosine to the sixth times sine of x. All right, so let where you're going kind of guide you. We're going to deal with our left-hand side and try to make it look like the right-hand side. Well, I have this single x sitting out here. So what I'm going to do is separate this into sine squared and another sine and just stick it on the back side so that it sort of looks a little bit like what we're doing here. Okay, so right now, this and this match. I also have a cosine here, and these are all in cosines, right? So this is in cosines. So I know I need to change this into cosines because there are no sines left over. And sine squared is an easy switch. So if I take the sine squared and make that 1 minus cosine squared, and that's times cosine to the fourth times sine of x, and that equals cosine to the fourth minus cosine to the sixth times sine of x. All right, so what I'm going to do here, I need a cosine of the fourth and a cosine of the sixth. Well, I can get that if I distribute these. So I'm going to distribute and get cosine to the fourth minus cosine to the sixth. That will be in parentheses. And then I have this sine x hanging out on the end, and that will equal cosine to the fourth minus cosine to the sixth times sine of x. All righty, so what's going to happen here is these take a ton of practice. They take trial and error, more error than trial. Ignore that thing that just popped up on my screen. Can I make it go away? Oh gosh, that's not what I want to happen. Go away. They take more trial than error. So when you make a boo-boo, just keep trying and don't get rid of stuff. Keep it. Don't scribble it out. Make sure we can read it. We need to be able to go back and look for your mistakes. There's going to be lots of little 10 problem sets. I've been working them out. I can send you hints. I have no problem doing that. I'll be happy to help you out in class. But I would definitely get ahead because these are a little bit time consuming. And even though there's only 10 problems, they're a lot of work. But they're going to make you think outside the box a little bit. So if that's a challenge for you, these will definitely make you think and know that the next section, things get a little bit easier and you kind of go back to some formulas and hopefully the thinking will get easier after this. All righty. All right. Well, toodaloo.